Okay, so today we're going to talk about, continue on our discussion. We were talking about the Fireant FPGA, and today I want to look at the Uart Demo. Now, the Uart Demo was designed for a different chip, so I didn't quite get it. It's not quite working as such, but what I am going to talk about is what a Uart is. Give a little discussion. I'm going to go over their, let me add this scene. We're going to, so we're going to go over, I guess we'll start with the Uart guide. Let me bring that up. So this is the guide that they provided, Efinity did to their Uart core, which is basically code that creates a Uart in their FPGA. And as you can see, it's basically you have a transmitter, a board generator that is what matches. Now, first let's go over what Uart is. I think I didn't get into that. Uart stands for Universal Asynchronous Receive and Transmit. It's what it does is it takes a parallel output and serialize it so it can easily go through and go to another device. And if you've played with Arduino, it's very common. That's how you get your output to a screen via well, you get it through a serial connection, and Uart sends data through a serial connection. So the nice thing about Uart is there are only two wires. There's the transmit, and there's that goes from out one device to the receiver the other, and back and forth. So that makes it very easy to connect. You just got your two wires, and the transmit transmits the receiving input. The receiving input gets it, does what it does, and sends it back to the transmitter, to the transmitting, who gets it through their receive input. You can see here, transmitter, receiver, board generator. This is important. They have to be within 10% of each other. So if you've ever set up a serial terminal and all that comes out of it is garbage, it's probably because it's not set at the right board, or I think it stands for bits per minute, or bits per second or something. It's basically the speed. So, let's see. So this is, you have your clock, you have your reset, transmit data, transmission process, receive, data valid, all the different ports involved. But again, between two devices, there are only two wires. So let's look at the components here. Board generate block generates a board ticket 16 times the baud rate. You configure the generator with the board parameter. So we're going to use, we generally use 115/200. The transmitter block takes the TX data and serializes it, which means takes all the bits and they make them go straight in a row and sends them to the receiver. Now the receiver is interesting. The receiver is based on a state machine, and the state machines are one of the ways it's very popular in terms of designing FPGA type programs. So you have the idle state, you detect the start bit. If it's invalid, you get an error, you go back to idle. If it's valid, you start processing until you get the latest data bit. And then you get a stop bit, and if it's valid, then you go back to idle. Either way, you're going to go back to idle, but in that point, but you may get an error if the stop bit is invalid. Now, there's also something called a parity bit, which is used to make sure that the data wasn't changed along the way. So they had this guide that I should put in the link. Goes through the UART data form start. Here's all your data, and that's one limitation of UART. It's basically 8 bits at a time, because if you start your data, well, these are all your little 8 bits of data. This is your 8 bits of data, your parity, and your stop. So, and here's your clock, you receive, you get the data valid, let's see, shows when reading data, shown when the received data, when is valid, that's, data is valid, and then so this data has been come through, it's valid, and then it's no longer busy. So that's your receive operation, and they go through it. When error goes high, the valid here goes low because you have an error. So valid never goes high. And when there's parity error, so this is a separate type of error. And when this goes high, and it goes low on the next received byte. Bits can be changed, so this explains here why you would want to look at it, need a parity bit. And UART is a very old design. We've been using it, serial communications in computers, for some time now. And the next thing they go into here is the example design, which we're going to take a look at. And it was designed for the T20 BGA 256, which has 8 LEDs. We only have 4, and I think this is part of the heart of the problems I ran into. So the idea with this, what's supposed to happen is, once you set up your terminal, it has a particular, so if this is the example, they go through the command. So if you set 3 zeros and a 2, that's where you're putting it. The first for writing, writing out, where you're writing out and what you're writing out, separated by an exclamation point. And by entering the controls in the commands into the LED, the commands, you can control the LEDs, which is a little hard to do when you only have 4 LEDs. So I believe that's one reason why it didn't work. And it goes through, this is the design, what's mapped to what. And one of the things I had to do to just get this thing to run, or to synthesize for this board, is I had to change this up. Now, another thing I might be able to do is, since I don't have 8 LEDs on the board itself, I can take the GPIO and connect it to 4 of the LEDs, and that might be an experiment I'm going to try. And if I get that working, I will present it to, show you what I did. We'll talk what I did to get it to synthesize. So this goes through the example. But let's take a look at it. Let's switch up here. We'll look at that one. Yeah. So this here, back to our Efinity software. And notice, when you go to the project, there are quite a few files. I guess this defines the registers for the user data. You receive, how that receive state machine works, the top level of the Uart and notice that it is creating the receiver and transmitter, and resets the command. So this is part of the demo. So this is what looks at those commands and decodes them. And here's our decoder and encoder. Board generator, this is part of the Uart. And this is how we get the board, the board rate. LED control, and this is what I changed to 4. Again, I might decide to change it. If I add 4 LEDs and then make it 8, that could go a long way in getting this thing to work. Uart defines. This is basically all our definitions that go throughout the design. So if you notice, pretty much all of these things include this Uart defines. What I had to do to get this even synthesized, because I knew it wasn't going to synthesize how it was, especially when I realized it was for a different board, different chip even. And what I had to do is use a tool in here called the Open Interface Designer. So let's take a look at that. Let's see if I can, there we go. Little paintbrush symbol here. So this is what you use to create your constraint files. Constraint files are very common. You use them. Basically what it does is it maps the chip to outputs or to different things on the board, like the LEDs, like buttons, like whatever it is. And most FPGAs companies have you able to download the like a master file. I know all the digital input boards have that tells you what pin is attached to, for example, an onboard LED or an onboard button or whatever it may be. The GPIOs, like in this case, you can use. So this is first thing I had to, what I did and what they recommended you do when you start a project for the Fireant is I created a new project. They recommend you copy, there's a file called, let's see if I can, there is a file, and I don't see it in here. It's, let's see if I can open it up in here. Can I open a file? Or do I have to bring up, yeah, let me bring something up here. Let's see what we got here. Okay, now this is what I want to show you. This is the master file, and they call them whatever the project name, or in this case is the master, they call it Fireant Parity.xml. And this defines everything, the LEDs, I/O, it defines all the GPIO. And this is what allows you, this is what's used as the basis for when we go back to here, to create our package or design. So when you look here, this tells it, we know the device, the package, the timing model, the location, and you can define your GPIOs here. So I had to change it to define these GPIOs for this board, whereas before it was designed to these LEDs pointed to the output ports on this other board that it was designed for. And I did this with these other things as well. I picked a transmit and receive port. I had to redesign this to map to the correct PLL, the buttons to their correct, and the proper GPIOs for the buttons, the LEDs, PLLs, all specified in these Perry files. They actually recommend you use the one from their counter example, but you can if you need something else, you can look it up in the master and put it in your PRR files, and it can read this XML file in, and it knows exactly what it has. And this is where a lot of what I had to do to get this to synthesize, making sure this was defined based on what I had rather than the original chip that it was created for. And once I did that, I was able to, it would synthesize. There is, let me go back to it. Here we go. So once I was able to do that, I was able to run the synthesis. And for the most part, there was an issue where there's still some pin that's not right, and that's not mapped appropriately. So I'm going to have to look at that. And in order to get this to work, I think the two things I have to do is resolve that issue. And I have to probably just use a regular GPIO and hook in an LED there. And hopefully once I do that, it might actually behave as expected. And you can see I got an unassigned core pin, one missing interface pins, and I have to figure out what that all is, what pins might be missing. So, so this is an example of, now, if you are dealing with a more advanced board, for example, if you are dealing with the ARTI, which the ARTI or the Zybo, they actually have that kind of functionality. I believe it's if I recall, they're just IPs you can just throw in, if not built into the microprocessor or the microprocessor. The microprocessor object. So let me see. Let me show you something here, and I think we'll finish our little discussion on We'll finish a discussion on UARTs on this. Let's see. Okay. Let's get this where we can see it. And okay, so we're back in Vivaldo here. And this is the Uart demo. And let me show you something here. Open block design. Now, in this case, this was a very simple demo. You had your input, you had your microblades. But you can see you were able to, this is from the microblade itself, a pin. So this is part of the microblade. So when you deal with a more sophisticated thing, they have these things already built in that you can just use. And that's what I wanted to show you. And this was a very simple example where you didn't even, I don't even think there was any code here. It just input, and I believe there was a more sophisticated one. Open. Uart. Let's see if Uart Demo 2. Let's open this and see. I believe this. I had done a Udemy class, and he did some Uart demos, and this is what this is from. Here we go. Design sources. Open block design. No, it's the same thing. Anyway, you get the idea. There are basically two that the more sophisticated FPGA just have this built in. And so anyway, again, Uart is something that's been around for a long time. They basically allow data to be transmitted over very simple connections, such as a, simple USB, simple cables. And again, it's designed to take parallel data coming from the processor, turn it into serial chunks of 8 bits that are then reassembled at the other end. And the example that we did in Efinity had used a state machine to reassemble it, to look at all the bytes coming through and put them in the right thing. So basically what happens is you have the data coming out, you add your start bit, your stop bit, maybe a parity bit before send it across. The receiving system gets rid of the stop parity, reassembles it into a parallel byte, and sends it back to the processor. So it's a very simple way of transmitting bytes. It's been around for a long time, and as you can see, it's very commonly used in with your FPGAs. And the other thing I think was interesting is that hopefully you got something out of it, is what I needed to do to get this thing to synthesize using a different processor than the one that the demo was actually designed for. Again, I got to synthesize, I didn't get it to quite work, and I'm thinking there are a few ideas I have to correct that situation. I think starting with maybe giving it the 4 extra LEDs so that it could do what it needs to do. Anyway, I hope you found this informative. And if you do, please have a like, give me a like and subscribe. If you have any comments, any ideas, if you've gotten this, if you've actually gone through this and gotten the thing to not just synthesize but actually work, and put it in the comments, that would be great. So, okay, thank you, and that's all.